first saw these videos, I kind of sat there and kept watching and said, I think we can do this all with AI. To me, it's really cool. Alright, so that's some examples of AI learning to move their body, being able to interact with the world, developing their brains over time. Now, this next video is an example of AI learning to compete. Now, the thing about this is the mechanics underneath is all quite simple. Genetic algorithms and some neural networks running over time. And the key thing is some fitness function. Now, this research is from '94, so it's quite old. But what's happening is people are using this research for increasingly varied areas.
This final group of creatures was evolved for their ability to compete for control of a green cube. The creature closest to the cube at the end of the simulation is the winner. Here, a strategy first arose for simply tumbling towards the cube. Then one learned to block out his opponent. But then later, one learned to overcome the obstacle by climbing over it. Some pinned down their opponents. Some covered the cube with protective arms. Others simply unfolded onto the cube. The success of a strategy is often highly dependent on the opponent. Here is a hockey-playing creature, which takes the cube away and wins by a large margin. Here are two similar hockey strategies battling it out with appropriate gestures. This crab-like creature.
Okay. So that's some examples of AI lifestyles learning to move their body, and also examples of AI being able to learn to compete with each other, develop strategy in the world. Now, what I want to show you next is I'm trying to show you increasingly how these AI can develop increasingly advanced behaviors. In this next video, I want to show you some behavior of agents learning how to use objects and learning to cooperate. So in this one, this agent's learning how to use an object in the world. It's learning how to use this little platform to skate. And in this next video, we have two agents learning to work together, to cooperate, to push this bigger block. In this video, we have a group of agents using basic swarm intelligence to work together to find a target area. Okay, so that's some of the basic behavior these agents can do. So you'll notice that it's physical behaviors, moving their body, working together. But what researchers have been able to do now is take it a little bit further. They've been able to get these agents to emit signals to each other, receive signals, and actually create a language that becomes stable over time. So in this world here, which it's called a mushroom world, you have poisonous mushrooms and you have nutritious mushrooms, and you have a population of agents who actually have to explore this realm, learn to identify these mushrooms, and if one of them figures out that a certain mushroom is nutritious or poisonous, then we check about it. Now in this world, they've been able to. So an example of like a sense of this world is purple mushroom good. So the language is actually still very basic. In this experiment, different from the other one, in this experiment we have a group of 4 agents. So the small black circles in a world of 2 bigger circles, And these agents have a fitness function where they have to try and arrange themselves so that each circle there are two agents. And over time, what happens is these agents develop signals. Like, for example, I'm looking for a circle. I'm in a circle, but I've only got one person. Sorry, the circle's full. Go away. And you'll see on the right side here, over time, these agents develop. They get closer and closer to being able to navigate and get into the circles. Alright, so that's where evolutionary language is at the moment. It's still, there's still a lot further we want to take it. Now, the step further up, trying to do, in the mushroom world, there are certain abstractions or constraints, but I think that if we take those abstractions away and we force these agents to kind of work at it, then we'll do these concepts will make their way into the language. For example, in the mushroom world, if an agent sees a mushroom, so if there's a mushroom right in front of me, and I don't know whether it's poisonous or nutritious, the abstraction these researchers have done, because it's still very early research, is use a form of telepathy. So if I don't know this mushroom is nutritious, Sandra will look at me and we'll both know that I'm looking at this mushroom, and she'll just zap me in the answer. So that process of telepathy bypasses a lot of constraints in the real world. So in the real world, there's a bunch of mushrooms there. I have to convey which mushroom in front of me I'm talking about. I have to form the question. She has to volunteer to answer the question. And there's all these abstractions that don't happen in the real world. But if we take those abstractions away, we enforce physical constraints. Those being able to use direction. I'm hungry in front of me. Can you help me tell me if this mushroom's good or bad? My theory is that because they have to do that, those ideas make their way into the language. And on the right-hand side here, the language that these agents come out with is very specific because there's a specific fitness function as well. They have to get into these circles. So the whole language is about navigating and getting into these circles. So the language doesn't get beyond that. Okay. So what I'm doing at the moment is I'm taking away those abstractions and I'm taking away the fitness function. Now the problem is, if we take away the telepathy, if there's a mushroom in front of me and I want to know the answer and I can't reach into your brains magically, they have to cooperate somehow. So if you have a bunch of neural networks in an environment, you have to work out some way to get them to cooperate. Because if they don't cooperate, because you imagine a bunch of brains there, you can't tell them to cooperate. You have to provide some mechanism to get them to cooperate. So my idea is to make them mortal, make them to mortal life. They have to cooperate. They have to help each other because if they don't, they'll die and their genetic line won't continue. Same with the other experiment, the 4 robots and 2 circles. If there's no fitness function, they'll just sit there. If you take the fitness function away, you can't make them do anything. So again, we're modeling life. We're creating an ecology, giving them a body that they have to maintain, they have to reproduce and go and move on. So, I'm creating a need for these agents to be passing their genes. And as part